Hi, I'm He Fan from Zhejiang University. In this video, I will introduce our PointListNet, a deep learning method for 3D point list modeling. Let's go through the main idea of PointListNet. PointListNet can be used for protein and non-coding RNA modeling. Protein and non-coding RNA are large biomolecules and are essential for life. Understanding their function is significant for life science. These two kinds of data has a 1D sequence structure and a 3D geometry structure, which we call 3D point list in this work. For example, proteins are made up of amino acids, and those amino acids are linked by peptide bonds and form a chain, a list. However, protein functions only when it falls into a 3D shape, like antibodies attacking and fighting off antigens, or other proteins interacting with each other. It is mainly based on their 3D structure. Therefore, once we recognize its structure, we can know its function and attributes. In this paper, we first investigate a range of point cloud methods for protein understanding. Then, we propose a transform-style network, that is PointListNet, for 3D point list modeling. We conduct extensive experiments on two protein tasks, and the proposed method significantly outperforms the existing methods. Now, let's go into the details of this work. The goal of deep learning is to capture the structure of a certain kind of data via artificial neural networks. Usually, an element of a data includes a position part and a feature part. According to the type of element position, data exhibits different structures. Deep learning has made tremendous achievements on modeling different kinds of data, such as text, images, and 3D point clouds. Those data exhibit different structures. Texts are regular 1D list of words. The position is the word's sequential order in the text, and the feature is the word itself. Images are regular 2D grids of pixels. The position is the row and column where the pixel is located, and the feature is the color. Point clouds are irregular 3D point sets. The position is the 3D coordinate, and the feature is the point attributes. Proteins can be seen as a 3D point list. The position of an amino acid involves a regular 1D sequential order, the peptide chain, and an irregular 3D coordinate. The feature is the amino acid, the residual type. So proteins and non-coding RNAs exhibit both a regular 1D list and irregular 3D set structures, which have not been well explored in deep learning. We propose a transformer-style PointListNet to fill this gap. First, we think there is a universal rule or law that guides how to model the structure of different kinds of data. When deep neural networks tries to model the structure of a certain kind of data, it includes two steps: finding related regions and encoding related regions. For example, when we want to recognize the dog, we first find out all the patches that are related to the dog. Then we encode the related patches into a representation. This is also applicable to natural language processing. We first look for the related words to a question, and then encode those words into to generate the answer. When we developing a network to process 3D point list, we also follow this finding and then encoding law. So for finding related points, we use a non-parametric distance-based attention mechanism. This is because when employing transformer for protein modeling, we find that it may be the 1D and 3D distances instead of amino acid features that mainly determine the amino acids correlations. Self-attention may be not that effective. Therefore, we replace the self-attention in the vanilla transformer with a distance-based attention. For coding-related points, we propose a 1D, 3D displacement-aware value method to integrate relative structure modeling into transformer. When performing 1D, 3D displacement-aware linear transformations, we use different groups of parameters to reflect regular 1D order displacements, but directly encode 3D geometry displacements. For example, the P1 minus P2, and append the 3D displacements to the point features due to their irregularity. Moreover, when encoding the 3D geometry displacements, we integrate a rotationally invariant technique. We evaluate the proposed method on two recognition tasks: point cloud protein fold classification and enzyme reaction classification. Because PointListNet models both 1D and 3D structure, it significantly outperforms those point cloud methods. Note that even only with the 3D geometry structure, PointListNet still significantly outperforms the point cloud methods. There may be two reasons leading to the superior. First, those point cloud methods do not employ effective attention mechanism to capture point correlations. Second, they are not rotationally invariant. Our method also significantly outperforms those sort-of protein recognition methods. This is the summary for this work. Among the early efforts, we investigate a range of point cloud methods for protein modeling. We propose a transformer-style network that is PointListNet for 3D point-list modeling. We replace self-attention with non-parametric distance-based attention, which is more efficient and effective to achieve the correlation among microparticles in some cases. We integrate relative structure modeling into transformer and employ regular and irregular methods to capture the sequence and geometry structures. We conduct extensive experiments on two protein tasks, and the proposed method significantly outperforms the existing methods. Thank you.